Hey everybody, today we're going to make a brief introduction and look at some of the fundamental concepts moving forward that we're going to cover in the course. I'm Michel Maharbiz.
And I'm Vivek Subramanian.
Well, let's get started. So, as a broad, everyday motivating point, I think we decided to take a cell phone. And just think for a second about your cell phone. It's really a marvel of hardware design. And by that, we don't just mean, thinking about the chips that are going inside of a cell phone, even how the touchscreen works, the little microphone, how your cell phone detects when you move it, shake it, how it detects its position. All of these types of notions and devices that link everything from electromagnetics down to digital computation and, of course, software are just absolutely marvelous. And we want to give you a little bit of a motivator, right, to get you kind of thinking about these issues using the insides of a cell phone. And we're going to do that in a second. Vivek's quite an expert. But we want you to really just find everyday examples like this and ground them to some of the concepts we're going to deal with in the course. I think it's a lot of fun.
So having motivated the course, let's dive into a cell phone. And the cell phone in particular we're going to pick is the iPhone 3G. For no other reason other than it's a very well-known cell phone. Depending on when you're viewing this video, it's either a few years old or it might even be a few decades old. We don't know. But we've taken an iPhone 3G here. And this is a teardown of an iPhone 3G provided by a company called Semiconductor Insights. And what they've done is they've taken the board out of an iPhone 3G and they've taken a photo of the board. And you notice several things. First, you notice this sort of green plate on which there seem to be a bunch of components built. That's a printed circuit board or a printed wiring board. And on the printed wiring board, you see a whole bunch of these little black boxes. These are various integrated circuits. And you'll see several of different sizes, and particular ones I'm going to point you to are over here. You see what is called a Samsung application processor and DDR SDRAM. That is actually the brains of the iPhone. That performs most of the application processing. And then you see another chip over here, an integrated circuit made by Infineon called the digital baseband processor, and that performs most of the communications digital functionality. You also see several other boards and other components on this printed wiring board, and in particular, you see a lot of these little components that look like little rectangles with some colors on those. Those are passive components. Depending on which one we are looking at, they may be resistors or capacitors. And the reason we're pointing these out is you're going to learn about a lot of these through the course of this series. For example, very early on, we're going to talk about resistors, and then we'll move on from there to capacitors, and then we'll start talking about more sophisticated circuits built out of these components. So the goal of this course then really is to give you the grounding such that you can take one of these devices, and by the time you're done with this course, you'll be able to figure out a substantial amount about the functionality of these.
So when I look at this, what really gets me is that one might think that inside an iPhone is some big single chip, that Apple made that does everything. But, that's really not the case, even though maybe as phones mature that will happen a little bit. Look at the variety of companies and the variety of chips and how they're integrated. There's really a whole ecology of hardware design of various flavors and disciplines that really goes into building this phone. And I find that pretty amazing. So that leads me to a real quick question for you, since you're an expert on this. So I keep hearing, analog circuits, digital circuits, and that you can find both kinds in something like this cell phone. Are we going to talk about that? Is that true?
Yes, we are. So, for example, the Samsung integrated circuit or chip that we've been talking about is primarily digital. The power management IC, for example, has analog functionality, as do several of the other ICs, including some of the communication chips, as well as some of the power chips. So you'll find that there's still a great need for digital designers, and there's still a great need for analog designers. And in this course, we're going to give you a little bit of both.
Yep, and we know you don't know what analog and digital quite mean, maybe, but you'll get to that in a few slides. All right, let's move on. So here's another little way of looking at the systems inside something like a cell phone to kind of motivate some of the lessons in the class. And here we've taken a different approach. We're not showing you chips. We're showing you conceptual blocks that might be part of a cell phone's what's called a front end. And that means the part that's talking to the signal that's coming in and out. So in this case, we're talking about an antenna. And so this is the front end that talks to the antenna of your cell phone. So here you have the electromagnetic signals, the waves that are coming in, and this little line represents an antenna. Of course, the antenna can be shaped in many different ways. And that antenna is then going to connect via wires to a variety of components. And we're, of course, not going to talk about these components in any detail right now, but I want to point out to you that these components are all broken up into boxes. So just look at that very simple notion. Here we have an area of boxes that we call the RF front end, and you've got a filter, a couple of filters in fact, and here these little triangles you'll come to learn in this class represent amplifiers. They boost some property of the signal, and then these things mix up signals and so on. This thing here generates a particular sinusoidal signal, voltage signal. And then it moves on to this intermediate block and then to what's called the back end, and eventually it goes into things like analog to digital converters and it's formulated into speech, for example, if we're just talking about audio. But the point here is not what they do today. It's simply that they're broken up into boxes. And so it's going to be very important in this class to become comfortable with the idea that some of these circuits, these linear circuits, can really be abstracted out and their properties be represented by black boxes that are simpler than what's actually in here. And we're going to touch on that in the class in a number of points. This idea that the abstraction allows us to really not only simplify, but let's say I'm the guy that does the RF front end and Vivek is the guy that does this IF block. Vivek probably doesn't want to know every last little detail about my RF front end. There's got to be a way that we can pass to each other just enough information to make the design possible. The other thing I want to point out is that this idea of breaking up very difficult problems, into hierarchical blocks and into black boxes, into modular blocks, is really, really fundamental to very sophisticated high-end hardware design. This is used everywhere from processors to very difficult analog circuits. This divide and conquer, this idea that you come up with conceptual tools that allow you to simplify or reduce the scope of a problem and solve that one and then go on to the next one and then eventually you solve the whole thing.
So is that how, for example, when we looked at that cell phone board and we saw it had a lot of chips from different manufacturers, is this abstraction idea what allows someone to combine all these chips from different manufacturers in that way?
That's exactly right, and it happens at multiple levels. So the person the team that's putting together the board that includes all these components, that really the architecture design, has a sort of a reduced amount of information about what's going on in each of the individual chips, but it's certainly a rich enough information that they can then design the board. And likewise, within the chips, various teams break up and do the different components of the chip. And for example, one team might do, say, this component, and another team might do this component. And in this way, they can communicate just enough information to break up these difficult problems. And so this is why you get these sort of hierarchical structures in the companies to build these things.
And before we move on, I should add that very early in this course, you're going to learn some of these sorts of techniques for simplifying and putting into hierarchy circuit constructs like this.
Definitely. All right.
Okay, so we've now introduced what this course is about. This course is ultimately about circuits. It's worthwhile then to talk about what you're going to learn in this class. Fundamentally, at the start of this class, what you're going to learn is you're going to learn, if I give you a circuit, I will ask you to figure out what that circuit does. This procedure of taking some circuit that you're given and determining its functionality is called circuit analysis. And so in the start of this class, what you're really going to focus on is circuit analysis. In other words, we'll give you circuits, and we'll ask you to figure out what they do. And that is analysis. The reverse process is obviously also extremely important and possible. And depending on whether you're taking this class remotely or you're doing it through the lecture hall, particularly if you do our labs or if you're taking lectures where we actually go through this, you'll also deal with some design aspects. Specifically, that is the reverse process, where I, as the customer, will give you some specifications. I will tell you, I want a circuit that produces an output of arbitrarily 4 volts. And then you'll have to design a circuit or use synthetic approaches, in other words, synthesis, to create a circuit that does just that. So in a sense, analysis and synthesis are complements of each other.
So I think this is a great time to take a little break and look at some history. And we're lucky because Vivek is somewhat of a history aficionado in the early, about the early days of this field. And so I thought I would take a back seat and let Vivek just chat away on some of this stuff and ask him some questions, and then we're going to wrap up at the end with some concepts related to this to wrap up the module.
Thanks, Michel. What's worthwhile to start, because we motivated everything by cell phones, is talking about what life was like before we had cell phones. In fact, before telephony itself was particularly prevalent. And most of you have probably heard of the telegraph system. And the telegraph system has existed for well over 100 years at this point. And telegraphs were used to send messages over long distance, and they were encoded. So they were typically encoded using Morse. So you've probably seen movies where you saw people pressing on Morse keys like this. And when you would press on a Morse key, a specific signal, typically a beep or a click, would be heard on the other end. And then using those Morse keys, someone who could understand Morse code on the other end would then decode that information, and you'd be able to send messages over long distances. So Morse was very important in the early days of communication because it enabled communication to occur over long distances where previously we depended on messages to be transported over long distances. Note that this is Poly Express. It should say Pony Express. So the key then at that point, now this goes back before wireless. So to communicate signals, we actually had cables. And what cables did was they ran along existing train tracks because the train tracks were already there. The land had been cleared for trains. So cables would be run along the train tracks, and so they would provide information right along the train lines.
So let me ask you a question. I always wondered this. So when they press down on the top of that paddle up in the figure you've got there, so what were they shorting the tip of the paddle to the bottom contact?
Yes, in fact, we'll talk about the specifics of open and short circuits soon, but these are conductors, so these are metals. And when you touch them together, a circuit would be closed, and that would be used to generate a signal on the far end of the wire.
Brilliant.
So, talking about cables then, it's really interesting to look at how communication was done on a global basis. In particular, at the time, by far the most important communication was across the Atlantic, between North America and Europe. And cables at that time were actually laid at the bottom of the ocean. And here you actually see a photo of the part of the pulling of a transatlantic cable. And that was completed in 1866. It didn't last very long. It had errors and failed pretty quickly. But this enabled telegraphic communication to occur across the oceans. And to be clear, we still use cables like this today.
So, yeah, that's true. But isn't it true that we, really have laid cables that have fiber optics in them? In other words, they throw light across instead of moving electrons?
That's exactly right.
Oh, okay.
We still have cables today, but to a large degree, communication has now been largely replaced by using fiber optic cables. And those are still laid. In fact, in many cases, they are laid on exactly along the same paths that the original metallic cables were laid.
Very cool.
So then let's talk about the first wireless broadcast, so to speak. And credit for this is often given to Marconi and to several other people. But the original radio broadcasts were essentially like this. What you have is you had a spark gap, and the spark gap was connected to some sort of antenna. And what you would do is somehow you would generate a spark across this gap. So there would be an arc across the gap. And most of you have heard this. Let's say you're listening to music and you plug a speaker into an amplifier, or you unplug the amplifier suddenly and you hear the speaker make a crackling sound.
Yeah, definitely.
And in fact, that is because when you suddenly rapidly disconnect an electrical signal, it generates a broadband electrical stimulus. And if you connect that to an antenna, then the antenna puts out a broadband electrical stimulus.
Oh, so they basically broadcast this electrical signal caused by the spark.
Correct. You'd get a spark, and the antenna would essentially then give out a burst of electromagnetic radiation. Huh. And now the interesting thing to note is this was not tuned. So it worked fine in those days, because in those days there were not a lot of radios. But if you tried to use this technique today, you'd be disrupting all the radios around you. You couldn't have nearby signals.
Huh.
And so you get a spark, and you get the sound out. Now, what's really interesting is the first live sports broadcast was actually used to cover America's Cup yacht race of 1899, and Marconi essentially contracted with the New York Herald and the Evening Telegram to essentially give information about the status of the yacht race.
And this was done really out of the kindness of his heart, right?
That's to a large degree correct, except of course it's not quite so simple. He there was money involved, and that's still true. Economics certainly drives engineering, and we often design things ultimately with the goal of realizing products.
Sure.
So far we focused on relatively simple ideas using spark gaps and antennas, and those are things we'll talk about. But clearly the next big step to talk about, and we will get to this a little bit in this course, is the idea of the transistor. Now, the transistor was invented at Bell Labs by numerous researchers. The three in particular who are given credit are William Shockley, John Bardeen, and Walter Brattain. They did receive the Nobel Prize for this work. And this was done in the late 1940s through the early 1950s was when all the initial results came out. And the transistor is remarkably important because the transistor can be used as a switch. It can also be used as an amplifier. We'll learn about that as well. But think about that spark gap. In our original spark gap case, we had to somehow create that spark. Well, now we have a way to do it with a device that we can build and control electronically. And now Michel's going to pick up from here, and he's actually going to talk about taking one transistor and extending beyond that.
Yeah, so this really gets to the next big innovation, and I think at this point it dovetails nicely into things that all of you have probably seen at some level, and by that I mean what you call, chips. So there's this notion that we call the integrated circuit. So the first integrated circuit was invented by Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor, and they later went on, or Fairchild later went on to have a big part in founding Intel. And if you look at the patent application that Kilby submitted, you can read that his device was described as a body of semiconductor material, and this is the key part, wherein all of the components of the electronic circuit are completely integrated. And he received a Nobel Prize for this as well. But let me try to flesh that out and tell you why it's so important. So in most of your high school labs and in labs that you do in your early college days, you will take things like resistors and capacitors, and they're discretes. They're what we call discretes. They're actually a whole capacitor or resistor or some other component, and you're holding them. And you'll put them down on a board, and then you'll use wires to connect them by hand. Okay? Now, imagine how error-prone that would be if you were doing that for 400 million parts, even if it were automated. Okay? Now, just think about that. And now, the contrast to that, this concept of integrated circuit. So what's an integrated circuit? An integrated circuit is the idea that at one time, through a series of processes that are chemical and physical, you can essentially lay down all of the patterns for these transistors at the same time with all of their wires. Okay? So it's a little bit, it takes a little bit to grasp this until you've seen one and you've seen a little bit of it, how it's done. But we will go into this in the class enough to give you a sense of it. So here's what we call a die shot or a chip shot. This is a picture of what's inside those little black chips that you saw all over the iPhone and inside your computer. And if you open that package, which is a plastic or ceramic, you'll see this square thing that we call a die, and it's going to have little wire connections that go out from it to the package and then from there to the outside world. But the important part, what's in here. In here, you'll have hundreds of millions, in some components in modern use of billions, of independent transistors and components that are wired together. Now, this was not done by independently gluing in, 600 million things and then automatically sort of wiring them together. That would be incredibly error-prone, and moreover, you would have a lot of error even in the component values. The beauty of these chemical processes and this concept that Kilby came up with and Noyce is that we can build them all at once, and in the end, you have this integrated chip. This is why your processors cost really as little as they do.
And I should also point out that cost is another big benefit of this. You can build that 100 million or 500 million transistors on that single chip for just a little bit more than it costs to buy a discrete.
Absolutely, and that's the beauty of it. This is exactly why you can buy processors that do what the games that you like to play for as little as they are. So when you're building, a complex circuit, most of the failures are going to occur along all of the wiring and connections that are made. Again, even if these things were automated. So here's a circuit board with a lot of discrete components, and these things are sort of wired together on the circuit board and also by these wires in some way. And you can imagine what a mess this would make if you had a large number of components. Now, printed circuit boards, or that green substrate that you saw at the bottom of the iPhone, that holds together the iPhone components, that helps. This is sort of a way of automating and printing out the copper wires between individual integrated circuits. But they're physically very large, and the discrete components are very expensive. There really is no equivalent to integrated circuits to be able to build the technology that we all rely on right now, that are affordable, as Vivek said, in mass production. Now, that last point, I think, is absolutely worth stressing. Without integrated circuits, we just wouldn't have any of the technologies that you are all familiar with in everyday life. Not just phones, but all of the computation that goes into almost every object you deal with in modern everyday existence. So let me talk about circuits more broadly, and then dive into analog and digital circuits. Okay? Now, very basically, when we use the word circuits, we mean devices, and we'll define a whole bunch of devices in this course and give their electrical characteristics, but devices that are interconnected to perform some useful function. We say that thing is a circuit. And the term circuit can have uses outside of applications where you're purely moving electrons. But of course, in this class, we're really going to be focusing on that. It's things that move electrons around to perform useful functions. So, simple examples. A switch and a light bulb connected by wires to a power supply, and so you can sort of turn the light bulb on and off with a switch. That little spark generator in your car engine, your radio, cell phones, computers. But really, there are circuits in so much of what we deal with these days. Even our shoes have circuits to light things up. That it's in really everything. Moving electrons has just become a fundamental part of our society and our civilization. Typical circuits contain a lot of devices, okay? And so this gets back to the topic we touched on at the beginning of this module. How do you deal with that much complexity? Okay, and so there's really 2 points, and we touched on them before. One is hierarchy. So you're going to divide and conquer. You're going to abstract out this complexity into pieces not only that are related to each other laterally, but have sort of parents above them and children below them in the hierarchy, so that different teams can work on them and talk to the other teams. And there's going to be a way that we discuss this, and we're definitely going to get back and give you tools for this. And even more basically, just the idea that large things are broken up into subblocks becomes incredibly powerful. And the fact that most of the circuits we're talking about in this class are linear is going to make that very simple.
And very early on, we will give you tools to start doing this hierarchical analysis.
Absolutely. So, okay, now I want to break up this distinction or discuss this distinction between analog and digital circuits, because it's something you hear a lot, particularly if you're going to become an electrical engineer. You're going to hear a lot about this. So an analog circuit really is interested in representing some signal of interest, either by the electrical current or voltage, and attempts to deal with most of that signal, okay? And you'll see what I mean when I contrast it to digitals. So a typical analog circuit, for example, might be an amplifier. So it's going to take a weak signal picked up by a microphone and take the entirety of that signal and amplify it, or do something interesting to that entire signal. A filter, think of your stereo system. So you might want to play with what frequencies are coming out of the speakers from the recording or whatever sort of sound file you're dealing with. And you might run it through a filter that will remove, say, noise, or change the frequency components, put more bass on yours, coming out of your speaker, and so on. And so these things are all analog functions and analog circuits. And you can, of course, perform mathematical operations on these things. You could perform analog multiplication and differentiation, integration, subtraction. In fact, the early days of computation relied on analog circuits to do this.
And just so that you don't think that we're only talking about arithmetic with respect to those operations, later in the course we're going to give you some examples where we're going to take some sound effects boxes, such as are used for guitars, like distortion for producing a distorted sound, and a wah-wah, and we'll show you how those are built, and those are in fact mathematical operations that are performed on a waveform.
Yeah, that's a really good point, actually. You can perform all sorts of interesting things that have useful sort of everyday effects. So Analog circuits are, are to some extent susceptible to noise and distortion in a way that the digital abstraction deals with. And so this is always the plague of the analog circuit designer. It's also true that analog circuits still, despite great attempts at automating, really have a great deal of art and design to them. And this makes it very attractive to young hotshots like yourselves to go into analog circuit design and be the next person to really come out with that beautiful new analog circuit. Corollary to this is the fact that unlike digital, where automated design has been very, very successful, in analog design there have been some limited successes, but largely it's just not that easy to have a computer design analog circuits as well as a human.
Okay, so having talked about analog circuits, we can now talk about digital. In a digital system, rather than having continuously variable voltages where we perform operations and waveforms, here we break things up into discrete voltages. For example, if we are talking about a binary system, and most of you probably learned about binary somewhere in high school, we might have two levels, a level 1 and a level 0. And then we'll assign those to two voltages. For example, we might say level 1 is 1 volt or 2 volts or 5 volts, and level 0 is 0 volts. And now, the beauty of that is we don't have to worry about what's going on in between so much. We just have to know, are we at 1 or 0? And now we call, in the binary case, we call these bits. The word bits comes from binary digit. Now, once we've defined things into these sorts of bits, we can perform logical operations, so to speak. And you may have heard about some of these logical operations. There's a system called Boolean logic that we discuss in various classes. And we perform operations such as AND or exclusive OR. And these are so-called combinatorial or combinational logic systems. And we will talk about these more later in this course.
So just so I get the difference, at least at this point, between digital and analog. So a digital circuit is dealing with voltages and currents as well, right? But what you're saying is that it kind of ignores anything that that isn't part of the abstraction. So for example, if the signal goes up to 5 volts, let's say 5 volts was R1, and wiggles around a little bit, the digital circuits are a little bit robust to that? Is that what you were saying?
That's right. To give you a specific example of that, let's say we had that 5-volt system that you talked about, and its 0 is defined as 0 volts, and its 1 is defined at 5 volts. The system might just decide that anything above 2.5 is called a 1, and anything below a 2.5 is called a 0. So any wiggling that happens around 5 or around 0, you get to ignore. That also makes these systems really, really robust, so small changes in the voltage don't mess things up.
Oh, I see. And so that's really what we meant by, in the analog slide before, that the analog circuits were a little more finicky when it came to...
That's correct. And by the way, that's also why it's possible to build digital systems with billions of transistors and have them work, because we're just more robust overall.
Got it.
And so we can perform more sophisticated operations. So for example, we can perform math. We can build digital systems that perform addition or subtraction or multiplication. We can also create memories. So we can build systems where when we store information in them, they'll stay there till we lose power or till we read them. And so it's possible to build fairly sophisticated systems. And the reason we can build these sophisticated systems, as I just mentioned, is because digital circuits are robust against noise, so we can build sophisticated things.
So I guess I skipped ahead there, so I apologize. But let me add one last point before we get off of this. So I hear a lot about mixed signal circuits. So what is that? Is that somebody that puts all this stuff together?
Oh, well, a mixed signal circuit would just be a circuit that has both digital and analog functionality within it. It is certainly possible to put these things together. When we talked about the cell phone, you saw the example of a D to A and an A to D converter block. That's a digital to analog and an analog to digital block. In other words, if you use one of those, one or the other, you can have a system that has both analog circuitry on one side of the A to D and digital circuitry on the other side, for example.
I guess as our devices, on my cell phone has every day more little gadgets that interact with the real world. So I guess mixed signals would be pretty important as we go from all those sensors down to the digital.
Absolutely true. Mixed signal is extremely important today. It's an important skill to have. And in this course, we will try to teach you a little bit about both. Now, it is worth pointing out, and this is something most of you have seen, that we talk about clocks when we talk about digital systems. For example, when you buy a computer, it's given a certain clock speed when you buy it in the specs. Well, clocks are used to simplify design. What the system basically does is it synchronizes all the operations. And so when we say a digital circuit is clocked, we're referring to that synchronization, and specifically the periodic synchronization that occurs.
Makes sense. So let's wrap up, I think. I think you guys have gotten quite a bit of information today. And this last bit is maybe a bit dry, but it's going to help understand where we're going from here. So first of all, units. I'm not going to read every single one of these things, but it's important that you are comfortable with the SI system and the basic units of length and mass and time. Electric current we're going to talk about as the ampere. Not mentioned on here is the unit for voltage, which is volts, and temperature. So we're going to be extensively using this unit system. It's also useful that you at least familiarize yourself with the English prefixes, because Vivek and I will be saying microamp or nanofarad, and so it's good to kind of be able to instantly recall what that means. And you can, when we're giving you problems or discussing examples, we'll also make use of these symbol prefixes. So for example, if I have this little symbol in front of, say, a meter, then it would be a micrometer, which is 10 to the minus 6 meters.
And that's a Greek mu.
That's a mu. And so a nano is the same thing. If I've got, nanofarads, that's 1 times 10 to the minus 9 farads. And so we'll be using this all the time. Another note on notation, which I think is pretty interesting right before we wrap up. If you see us using lowercase letters for current or voltage, in this case, for example, current, we mean that we don't really know, or at the moment we're not really ascribing whether or not that particular variable is time varying. We're just saying we don't know. It's the general case, okay? If we put a parentheses t, right, implying that I is a function of t, then we're specifically saying it is absolutely a time varying quantity, and that's important for what we're discussing. When that's not the case, we'll use an uppercase letter. So if you see an uppercase I, it means that there's a DC current, in other words, a current that does not change with time, and we'll talk about that in the next module. And if you see an uppercase V, same thing happens. It's basically a voltage that's not changing with time. And boldface uppercases are going to have very specific meanings that we'll run into later in the class. At the moment, at the very beginning, we won't use this very much, but this might mean a matrix or a particular transform or a phasor, all of which we use extensively near the end of the class.
And as we put this together, you'll see how these things relate to each other. The way we're going to teach this course is pretty simple. It's as follows. We're going to start by teaching you things that don't change with respect to time, and that's DC. And then we'll start introducing concepts involving things that change with time, and we'll work into signals that are transient. In other words, they change with time, and then we'll talk about AC. So all of these will come together, and so this is a good starting point for all the analysis that we do.
All right, we'll see you in the next module.